sort of injecting nanoparticles into a fetus, but certainly the ability to scale things down so that we can actually do things, will potentially help in that arena. The flip side of it is I'm actually part of this maternal fetal toxicology program, which is looking at the impact of nanotoxicity on maternal fetal health. So there's some issues again that we don't know anything about that side of it as well.
Hi, you mentioned that some of these nanotechnologies have already been applied in marketed products. And in pharmaceuticals today, there's a big tension between the consumers and the producers over cost. And on the producer side, they say, well, we need to fund the research. So I'm curious, for these companies that are applying the nanotechnology today, how much of their revenue is coming back to institutions like yours to fund research? And if you can also give me a sense, how much of the research is published in open forums and how much of it is held privately or proprietarily?
Well, anything that's academic, it's all published. So we can't do anything, at least at the UC system right now, or at least where I am. I have this, anything that I do is published, whether that's supported or not supported by industry. I think at this point it's interesting because the pharmaceutical companies in-house are not necessarily developing the nanotechnology. They're really waiting for the academic community to get to a point where it's mature enough where they can sort of take it and not really have the risk of the technology, but be able to sort of repackage their drug or make it more effective. And the people who are developing it for the cosmetics industry or more the consumer industry, we have very little interaction with those, and they're generally very large consumer product companies. So I'd say very little research money gets packed into the university from that perspective. But we also, it's much easier, from a scientific perspective. The NIH or NSF is going to fund things that are making a difference more on the medical side than they are for making a better sunscreen or something like that. So we're really driven by, addressing biological challenges on that end as opposed to maybe, sort of making money for a product that's already there.
Good, so I want to take one last question, but it's just about 8 o'clock, so we're going to take a break. But I want to get this one last question in because I promised that I would get it asked. So
I'm interested in the structural applications. How big a membrane have you been able to produce with it? Or has that even been a goal of your research?
It has, yeah. We do a lot of things with membranes. So, we can produce things that are, fairly large. They're not the size of this room, but they can sit in, water filtration units, or they can sit in sort of plasma fractionation. We have a big project working with the Cleveland Clinic on creating an artificial kidney, a smaller dialysis unit that's more portable using nanomaterials, because instead of going to the hospital, having the costs of the hospital and hooking up to infusion pumps and having the big dialysis unit, you can have something that's portable that can be taken home. That same basic technology, but now we're shrinking down the membrane, making it more efficient and having better separation. We can make the package much more, sort of compact. So in that, I think the practical applications can reduce some of the costs associated with healthcare, but we have to think outside the box in some of these.
good, so we want to definitely give our speaker a little round of applause there. And I'm sure she'll be happy to be able to sit down for a few minutes. So we're gonna take a break, but we're still serving drinks and food. So please, if you're hungry or. This video, it was produced by PBS, and they were talking with a professor down at Rice University in Texas. But just to get the conversation going, this is another professor who's working on nanoscience, like I said, down in Texas. So it's about an 8-minute video, so let's watch it and take a look at what they're talking about.
It's got an interesting look.
Exquisitely small. The tip of a pin
And we're going to move in on the tip and get smaller still. You see those little blobs there? They are bacteria on the pin. And then on the bacteria, you see that little speck? It's a few hundred atoms across. That teeny thing made news recently because it is an invention. It was built by a scientist that you're about to meet. And the fact that she is a she was also news because there aren't a lot of she's doing this kind of thing. And some prominent folks have wondered why. So here is her story. Naomi Hallis knows how guys think. Her ranch in Texas is way, way outside Houston in brush country, so it's a little hard to find. But as it happens,
one of our neighbors used to was a former penthouse pet, so she was a bit of a local celebrity.
So whenever Naomi needed lumber or whatever delivered, all she had to say to the delivery guy, any delivery guy apparently, was,
"Do you know where the stripper lives?" And they would all know. And so rather than going into long detailed directions, all I'd have to do is say, "Well, we're about 200 yards past the stripper on the left."
The ranch is for weekends. During the week, Naomi Hallis is a professor at Rice University teaching nanotechnology and applied physics, fields that are 90% dominated by men. But not here, not in her group. If you look around, it's about even, which is different for guys.
What else could I say?
And very different for women.
Being a woman has actually never been an issue for me in this group. You just forget about it, which is nice. It's a nice feeling because a lot of people aren't that lucky.
So how'd this happen? How'd Naomi create such an unusual balance? Even her husband, this is Peter, he joins the group, not as the leader, he's just one of the gang. Well, there's a story here.
You know, the best science stories are told backwards, okay? So
let's go back a bit. When Naomi was growing up, yeah, that's her, and so is this, she never thought about becoming a scientist, even in high school.
I remember very clearly in high school, although I was always at the top of my class in math and science, I was told don't take physics. And the reason I was told not to take physics was because if I ever took physics, I would never get a date.
So she didn't take physics, she became a musician. And one day she was wondering where sounds came from, and a friend said, well, acoustics requires calculus.
But of course you've taken calculus, haven't you? And it just kind of hit me like a load of bricks. In fact, I hadn't taken calculus. I'd actually bought into this myth that maybe I probably wasn't going to be very good at math.
But she was good. So at 20, she decided, you know what, I'm going to drop music and switch to something sciencey.
I thought, well, maybe I want to retool my career.
But what about her, her feminine problem?
No, I didn't have I didn't have a feminine problem.
In other words, you weren't embarrassed to do ungirlish stuff.
No, I was really butch, actually.
So she switched from music to chemistry and then, interestingly, chose a female-friendly graduate program at Bryn Mawr.
Bryn Mawr was certainly a place where women were 100% accepted.
And that's where she got her MA and PhD in physics, and she married.
You thought about doing that?
And when she joined the faculty at Rice University, Naomi found herself increasingly attracted by the world of the very, very small, the nano world.
This is a vial of gold nanoparticles, solid gold nanospheres.
They're so small you can't see them. They're little clumps of gold atoms. But if you can invent a clump that's hollow inside, it'll absorb a different color of light. And by changing the thickness of the gold shell, you can make it absorb whatever color you want. So look, here, what was once ruby red is now clear. Naomi's work was new and very interesting to graduate students, well, to men. Women...
For the first 6 years, I had no women whatsoever. And then I had one. And once I had her, I became okay. And then lots of other women began to join my group.
Which was at first kind of unusual.
We're changing that. It won't be unusual for long.
Women told women this is a good group. Naomi says, I never planned this.
It just seems to sort of happen. Maybe having all these women attracts the men.
So in the end, she gets a balance. But the growing gang of women at Rice were at first invisible.
For most of my scientific career, I didn't publish with my first name in the paper, and I was always N. Hallis. So many people knew about my work and had no idea I was a woman because they read my work in literature.
But when Naomi and her colleagues created nanoshells by manipulating atoms, then the world noticed. The New York Times, Popular Science, Profiles. Nanoshells made Naomi and her lab famous. And yet, even as a tenured professor, plus by now she'd bought the ranch, as successful as she was, one day when she was presenting her findings at a meeting at Rice,
A man walked up to me and in a very loud voice said, "Excuse me, are you the lady in charge of the coffee?" And when I heard that, I just turned around and I walked back to my office and I just sat there and, I almost burst into tears. This is ridiculous. I don't want to have, is it for the rest of my life I'm going to be mistaken for somebody who's in charge of the coffee? And then I said, no, I think I will go back there because I don't want that person to win. I want to participate in this forum, and I don't care if he thinks I'm in charge of the coffee. So I went back.
and the contacts she made at that meeting led to a business which she started with biology professor Jennifer West, and they are now injecting nanoshells into animals with cancer. So here, just for fun to demonstrate, we're using a chicken breast. The nanoshells will gather inside the tumor.
And once they're in place, then light is shined through the skin and down into the tumor site.
Warming up the nanoshells so they burn the tumor. That's the steam here.
And that's sufficient to kill the cells in the tumor.
So without radiation, with light, you can attack cancer sites.
That's incredibly non-invasive if you consider other types of cancer therapies.
These therapies are still being tested by the women and the men who have gathered around Naomi. But the women, she says, even now, have to struggle to stay in the game.
I always thought it was a generational thing. I always thought, well, when I was a young scientist, I thought, oh, those are the older people. They're like that. But when I'm older, then people won't be like that anymore. But they are.
Too often, female grad students drop out, lose confidence, struggle to balance children and family. Naomi, I noticed, does not have children, which made me wonder if that's about work.
No, I cannot have children. So it's not that we didn't try. I am absolutely, that's another thing that people sometimes do look at someone who's childless and say, well, you like science more than, children and flowers and, things like that, but no, I like kids too.
So what she doesn't like is that half the kids, all the girls, still have trouble making the life that she has made. That struggle isn't over.
Our speaker back up and make a few comments on this, but if she wants. But I wanted to ask for any questions. This is something, I was a scientist, and I certainly remember when I was doing my undergraduate and graduate work, there was a lot more men than women. Now I was in physics, so I just thought it was because it was physics. I looked over at the biology departments and the chemistry departments. There are a lot more. So I think it makes a difference as to what fields you're in, but it's really unfortunate that we still have, at least it seems amongst some older faculty, and I think in the video they talked a little bit about how it was a generational thing. They think this discrimination against females in science. And my question was, if you wouldn't mind asking, do you see something like this as something that we need to actively work on, which I think is true, but do you also think that it's something that it's just a matter of time too before these kinds of things pass out? Because I would guess that it seems, or at least I would hope, that our society is getting more and more equal amongst men and women. But I'm just curious, this is always something that we'll have to work on, but do you see at least some of it turning around? Or have we reached, an inflection point? And is it turning around? I guess that's what I would ask you.
Okay. So I think, what's interesting is that I think the good news is that now, at least in sort of these interdisciplinary fields, so bioengineering is probably the best engineering discipline in terms of getting women. And a lot of it is because, at least in the sort of hard sciences, for the women I talk to, they want something that's going to make an impact or a difference, or sort of be able to say, okay, I've helped out, in some way. And biomedical engineering is one of those fields where you can say, okay, I'm doing something that's math and physics, but I'm actually going to be making somebody's life better, hopefully. Having said that, I have about 50-50 in terms of men and women in my group, but still the numbers, once you get beyond to the graduate student, drop off dramatically. So the faculty, is still 10 to 15% in terms of women, and that even drops off. So as you get up the ranks, they're really at the sort of full professor level, only a handful of women. So, whether is it the field? I think there's sufficient interest, but it's a long pathway to sort of get through the academic ranks. In industry, it's a little different, but still, the numbers, as you become more senior, they really go. They're like, it's called the pipeline effect, where it dries up at the top. And so, it's a slow process, and I think the fields that people, I do a lot of middle school outreach and sort of even elementary school, because I think it really starts there where you begin to say, this is exciting. And so I think nanotechnology actually has the potential to sort of say to people, hey, here's a new thing that you don't necessarily have to be trained in this really single-minded field. You can really be broad. You can think about creative ideas. And it's not a field that's been around long enough so that it is really entrenched by certain populations. So we have an opportunity.
Are there any questions or comment about women in science? Oh, I'll come over to you. So
Not so much women in science, but it's a specific question about macular degeneration. Are you folks anywhere close to attacking the drusen that causes macular degeneration?
Yeah, so the question was about macular degeneration, which is basically a disease that causes blindness. The retinal photoreceptor cells degenerate because of buildup of this plaque-like material called drusen. And so once people get this stage, there's you can sort of delay it, but the end effects are going blind. And so we've been working on some approaches to look at that disease. Part of it is targeting drug delivery again and using some of these. So Genentech has a drug called Lucentis, which is an anti-VEGF drug. So it blocks blood vessels from forming, so you can stop the sort of formation of these plaque-like structures. And so we're looking at ways that you can deliver this in a more controlled sort of delivery device, but we're also looking at if you do contract macular degeneration or you do have the disease and you actually start to degenerate those cells, can you start to build up a new photoreceptor layer using some of these nanomaterials? So we actually have 2 projects in that area. It's a long way off, I would say, to actually making that a reality, in the sense that we have promising data. But is somebody going to be cured of blindness? No, I think we can halt the progression better than we are now. But once you're at that stage, trying to recover from that is going to be a huge challenge.
So we have a question after.
Are there other technologies like in the solar business, where you can use nano, and also you mentioned about lasers and other things like this?
Yeah, I mean, nanotechnology is sort of ubiquitous now in microelectronics, energy, fuel production, you name it. And at UCSF, of course, we're sort of the healthcare campus, so we're really focusing on that area. But if you go around the country, really everything from agriculture to energy production, have people who are looking at strategies that either involve the use of nanomaterials or the development of nanotechnology-based strategies.
We actually have one back here.
Okay.
I see a bunch of hands going up, so I'll make my way around to all of you.
Yeah, I do have a comment on the Women in Science and Technology track. I volunteer in an organization called MentorNet. I do not know how many have heard of MentorNet. And their organization actually is trying to match up mentors with mentees. And most of the mentees are really females, if you will. There's no discrimination, but really the female needs a lot of helping hand to go through the science and technology track. So the more helping hand to mentor, to at least impress them that science and technology is really a cool thing to do, and there will be a more balanced representation. And through a couple of generations, I hope that the ceiling will be broken.
No, I totally agree. I mean, actually, we found it's having role models and proper mentoring that are the best sort of predictors of success. And those role models don't have to be, I mean, they don't necessarily have to be women. I mean, men can be really valuable in terms of providing support as well. But it's really having a supportive person who says you can do it, as opposed to if you have a setback, well, maybe you're not cut out for this.
I might have missed one small part real quick, but you mentioned that in your group specifically there's 50-50, but when it comes to professorships, it's not that way. So what's the gap there? That wouldn't be mentoring, hey, these people already are in the science. What's the gap there?
Yeah, well, they're in the science, and they all successfully get PhD degrees, but then there's the big gap called tenure for an academic. So you usually do a postdoc, 1 or 2 postdocs, which are 3 to 5 to 10 years potentially. You're now in your sort of mid-30s. You're expected to, in that first 6 years, publish, get grants, have a research lab, have all of this stuff, which always coincides, again, if you have children versus, or, have a family to support and everything else. So timing-wise, it's a really tough decade to be sort of under the scrutiny because, especially at sort of large research institutions, the pressure to produce at a really high sustainable level is quite high. It's still the same as it always was.
Are there any other countries that you find are better than America? In other words, they've broken that barrier?
No, I would say actually, so in that regard, the U.S. is probably the most advanced. So in Europe, the percentages of sort of professors that are women are even, sort of in the single percentages, as well as in Asia. So we're doing better than the rest of the world on that front.
Okay, here we have a question up front.
So getting back to the science, I had a question about, once you come up with an application for the nanotechnology that's going to be used in humans, how do you go from the process of like developing a test and like what's the testing process in order for it to be used in humans?
So generally, so one of the things we like to do, and there's different ways you can do this, but we like to actually think about what's the medical need and then sort of develop the technology to address that, as opposed to sort of, here's a bunch of technologies, let's see what's going to fit, or how it can help. And there's some people who do it the other way around. But sort of once we've, I think in all cases, so the progression is sort of test tube, laboratory, in vitro experiments. Then we start to use small animal models, which are typically mouse or rat. You have to get to a certain stage where you can show efficacy and safety, and then you can think about going into sort of larger animal studies, which, depending on your disease, are pig or calf, cow, whatever. So something that's sort of representative of the physiology. And then after all of that is done, and you've again done enough trials and shown safety, efficacy, toxicology, you can go to sort of a preclinical stage where you're looking at patients that already have the disease that are not going to be treatable in any other form, and then it sort of goes from there. So, in best case scenario, you're still looking at 15 years where you went from here's an idea to where you're going to get a real product out.
So the follow-up to that would be, since you were talking earlier about the toxicology of it, is that kind of something you're doing along the way also, since you're using the animals already?
Yeah, so, I think sort of, since all of our things eventually are going to be going into a therapeutic application, we want to make sure we have it sort of done before we even go that way. Because if we see something that's not good, it's just not even worth our time to sort of start to develop that to a point, where we see it downstream.
Just to follow up on that, I wanted to ask, in your lab, this is a very long process. So the stuff you're working on, you're talking about, biological systems. Are we?
Right.
We're not even talking about rats yet, or are we?
We do talk about. So we do most of our things up to sort of the rat level, and then, as an academic lab, generally, and especially as a sort of a more engineering lab, we generally partner with either somebody who's already in the clinical area, has familiarity with the larger models, or industry. So once at that point we sort of say, okay, we've developed the science. It's not really science anymore, it's really testing. And so we go back to sort of, what's that next application we think about?
You mentioned, you mentioned fuel, energy, and agriculture applications. Could you give us a couple examples of those and explain how they would be environmentally beneficial?
So, gosh, they're so broad ranging. So in fuel, it's sort of going back to the synthetic biology in terms of using nanomaterials or bacteria that's producing nano material components to make fuel, refinery more efficient, or actually generating fuels that are more efficient. So it's not necessarily, some components of that are nano, and some are not. For agriculture, there are people who are looking into sort of non-toxic or sort of pesticides or other things that could be more nanomaterial based that won't have the toxic side effects that some of these things do. Also, being able to get more efficient cultures and more efficient growth of crops using some nanoscale fertilizers or nanoparticle-based fertilizers that have controlled release of different components. So there's a variety of things out there, and of course it's not my area, but it certainly, there are sort of centers of excellence in nanotechnology in almost every one of those fields.
Hi. I guess this is sort of a question that begs itself in that, with industry as a potential financing mechanism, and obviously, there's probably National Institute of Health and other organizations. For me, it's always follow the dollars. And I'm wondering if, like many academic organizations, that in selecting projects to focus on, if the projects aren't actually, sort of focused for you by where's the money and which direction am I going to be able to profit and be able to keep funding going for the research at the maximum level. There's money in cancer. Hey, there's money in cancer. And so people are going to look at cancer because people put money in cancer. And the same is true, with, I just get a sense that a lot of academia is fueled by, keeping the funding on a consistent basis.
Yeah, you're absolutely right in the sense that, one, I'd say, so nanotechnology became hot from a research perspective because the federal government decided to put a lot of money into that area to fund. So people who weren't doing it, it didn't matter what you were doing, everybody sort of ran into that field. So in general, just being in nano, it's one of those buzzwords, just like genomics was, or other areas that have become hot. And it's a problem in the sense that the most creative ideas aren't necessarily funded anymore. So we have to, you sort of do what you want to do, but you have to sort of do it in the guise of I'm going to treat cancer or one of the major diseases. And in fact, at UCSF, there's been we've had a lot of discussion about, how do we actually go after neglected diseases, or how do we do other things that aren't, necessarily the priorities of the government. And it's hard, because you either get private money or you get government money, and generally they're both at sort of odds to what the researcher wants to do.
Right.
But we can't do the research without it. So.
Right.
Just to follow up on that, I would say that it seems like there must be a market out there for people to get their training and then start a business, or go into again a free enterprise and try to market something, especially using nanotechnology for mimicking the spider web, right, to build like strong allies. So I'm certain that there's at least some market forces involved in this, so just because it's related to this, I was wondering, do you see a lot of people moving into technology from your field, or is it still mainly academia based?
It's getting there. So I think now you're starting to see particularly in the Bay Area, you're seeing a lot more interest in the venture capitalist and a lot more interest in sort of forming startup companies. But I think it's still a good 5-10 years away in terms of being at a stage where people think it's not risky. There's too much risk right now for the reward. And that, in general, biotech is that way. And this sort of adds another layer of risk to the whole portfolio. So a lot of people want to do things, and if you go to these business plan competitions, you see all these nano companies, but the ones that really are going to be successful have to still be thinking about really simple applications as opposed to, I'm going to treat X, Y, and Z.
You mentioned a couple of areas of like attacking something, a disease, or building something in the body. How about breakdown, like in heart disease, to take the plaque, break it down? And you mentioned the problem of also getting rid of the nanotechnology out of the body so it doesn't keep eating up the rest of the body. Is there a lot of research in that area?
There's not a lot of research. I will say that, getting rid of vulnerable plaques is one area that people are looking at from a nanotechnology perspective, both for sort of developing tools that can go in and scrape off those substances, but also for, again, creating stents that sort of eat away at those plaques, or are able to deliver drugs over long periods of time where you're stopping proliferation of the muscle cells that begin to occlude arteries. So there is the flip side of trying to get rid of or instead of building up the tissue as well.
It seems like, it's right on. Yeah, hi, it seems like the medical field up to this point has been rather analog, with all our technologies and so on, and crude in a sense. Is there experimentation being done with light frequencies in nanotechnology for the purpose of healing a variety of ailments in tissues in the body? Is that like the wave of the future? I envision like light sources being used in plasma and laser, etc.
I think so. It's not directly my area. I know there's an increasing interest in using light, optical, photodynamic-based therapies, things that are less invasive than what we sort of think about right now in the medical field, which is go in and, by brute force, try to get rid of whatever or heal. So in general, I think the field is going that way. How do we make it more patient-friendly as opposed to provider, clinical, or sort of doctor-friendly? And there will definitely, at least in my opinion, be this convergence between sort of technologies that can enable that, and then sort of other friendly approaches.
One of the problems happening with antibiotics these days is that they're going unchanged, that they're being excreted, they're going into the water tables, into the eye, everywhere, and you got these little nano gadgets that are so small. What's to prevent those from getting excreted and ending up in places that we don't want them? How is it possible to track these things and keep them from being from causing havoc?
Yeah, no, that's exactly, I think, one of the issues that we're starting to think about. Because just like a drug, they will be excreted, in some form or another, and both from the body, but also whatever you throw away, etc. So, there are, I know at least a handful of people who are actually tackling that issue and have funded research to look at. They've actually done some studies in several parts of the country and looked at sort of quantities of nanomaterials that are found in drinking water, etc. Because even if you're using cosmetics, these nanomaterials are already there, right? You're washing your face, it's already in there. So right now it's sort of an attempt to know how much is getting in there, what are the effects right now. And actually the nanomedicine part of it would probably be the smallest percentage, because really all of these other products have much higher quantities of nanomaterials that are already out there. So it's an issue that we are dealing, or sort of, in fact, unfortunately, I think dealing with after the fact to some extent.
Are there dangers already? The cosmetics, for instance.
We don't know. We don't know if there are. There have always been nanomaterials intrinsically in nature. I mean, so atoms are, they're sort of the building blocks of everything. So if you think about using carbon-based nanomaterials, it's already present in your water, and there are high percentages. But because they're engineered in certain ways, is that different than something that's naturally occurring? We really don't know that. And there are differing. There are some published studies, but not a lot of work has actually gone out there yet. But people are studying it.
Yeah, the question is about, you're talking a lot about how to do a lot of good with nanotechnology. Mm-hmm. Is there research being done on things such as using it for weapons or anything else of that nature? What are some of the things that we could be afraid of that this could cause?
Are you fear-mongering again?
Just getting ready.
To be honest, I don't know it. I mean, DARPA is, DARPA, DoD, all of these sort of defense things are certainly supporting the field. Most of what they're supporting is sort of protective stuff at this point for the soldier. So whether that's cream that's going to block out exposure, whether that's, soldier gear and armor and sort of artificial ways to rebuild tissue for the battlefield. That's most of what I'm aware of. But I'm sure there's this whole other world that I don't have access to. But I think with any technology, there are always sort of dangers if you use it in the wrong way. So genomics and genetic engineering versus traditional molecular biology, all of it has and will have the potential to do harm. But again, it's sort of how do we sort of move forward while combating that? And I don't know if there's a good answer to that.
I've got a question that's going to be, I think you're just going to have to talk about.
Losing it.
I'm kicking off this here and see if that helps. This is going to be a highly speculative
question. I don't want to be I'm trying not to be I'm going to ask the standard Grey Goo question, but with a twist. We had this discussion during the break. As you said, that there are a lot of nanomaterials that are already out in the wild. There are already a lot of nanomachines to an extent, in that bacteria and viruses have had a very long head start over us, and there are certainly a lot more of them than there are of us. I've been wondering, how do you view the Grey Goo problem in the context of there are already viruses and bacteria that have nanotechnology that are trying to turn us into them already? If that makes any sense. Is the question, when I think about it in my own head, I mostly think about where are they going to get the energy, where are they going to get their raw materials, is the energy problem there, is this something that if it was going to happen, nature would have figured it out already? Very open-ended question, very speculative.
Can I ask that you, either one, tell me what the ragu problem is? Grey goo? Well, I don't know what that is, so can someone explain that to me?
Go ahead. I'm not sure if I know.
The Grey Goo problem is one of the concerns that some people have about nanotechnology, in which you build self-replicating nanomachines which can then produce more of themselves, and then through some miracle of extremely futuristic science, turn all matter in the world into themselves, and everybody and the whole world become great. Very, very, very few out there.
Yeah, honestly, I think if you actually do any of the sort of calculations of self-replicating nanomaterials, it's theoretically impossible to do that, to generate enough energy to do that. From a pure, is it possible? I don't think it is, but who knows that? I mean, certainly anything that's out there right now are just passive materials that are just at a smaller scale.
I think we're up front with Angela.
So this might be too general of a question, but I was wondering if you could speak to kind of the implications of nanomedicine on the cost of healthcare or access to healthcare. Like, is it so expensive to produce nanomaterials that nanomedicine is going to be accessible only to those with a lot of money, or it's going to drive up the cost of healthcare? Is this too speculative, or maybe you can speak only about your work?
No, it's a great question because I think it is an important one. And I think it could go either way. So there are certainly possibilities of using nanomedicine to decrease healthcare costs if we can develop ways to do sort of non-invasive, easy, self-administered drugs that use less drug, which is usually the bulk of the cost is the actual drug as opposed to the carrier, and you don't administer it as enough that much. And so that's sort of a positive to lowering the healthcare costs. On the other hand, I think there will be a time where, every new technology is very expensive when you first develop it, to recoup a lot of the costs that went into developing it. So we may see sort of this, spike and then have the ability to produce them go down. One of the benefits of nano fabrication techniques in general is that they are scalable, in that you can create something, but you can create a lot of them. So once you sort of have a template, it's very easy to produce a lot of that material, if you will. So it gives you the possibility of being able to create large mass quantities of it.
We have time for only a few more questions. I have to keep this pointed at the front, otherwise it won't amplify. So if you have any burning questions, raise your hand now. We already have 2 in line. And as I'm walking, I'm going to ask a question. I like to do this. I kept hearing you tonight talk about way off. Anytime anyone brings up what does the future hold, way off. So give us remind us of what way off is. Like, maybe make an analogy of where this is relative to other technologies that have come to fruition now.
So, if I compare it to the first, the Pentium chip, or sort of the evolution of the computer chip, that took about 70 years to go from sort of the first inception of it to where we are today. If nanotechnology will be a longer time horizon than that. So way off. Way off means sort of beyond, I'd say 20 to 30 years, or sort of what I sort of see as my research career. It's not completely, probably the next generation of.
In other words,
this.
your son or daughter will be treating you.
You got it. Mine's pretty young.
Okay. Speaking of something maybe closer, I saw Craig Venter recently, and he's talking about very soon doing massive genetic engineering and taking on the petrochemical industry and changing the world. He's a very polarizing kind of guy. And then a week later, I heard the Vatican say that genetic engineering was wrong. So I see the sort of battle lines, those two big, so just want to hear your thoughts on that whole thing, which maybe you're a part of too.
No, I'm not, but there's a lot of people who are doing genetic engineering who would not agree with Craig Venter as well. So it doesn't need, I think it's sort of, those are two extremes of the story. Yeah, I don't think we're there yet, but certainly there are, industry now is capitalizing on and sort of thinking about it as the next wave of, whether it's the, producing biofuels or producing energy, thinking about using genetic engineering approaches. So it's not, that's much closer than, I would say, some of these nanotechnology approaches than, we think. It's pretty easy now to produce almost anything in bacteria in pretty high quantities. So again, it's not, on one hand, we've been producing things in E. coli and bacteria like antibiotics for hundreds of years, or tens of years, about 100 years. So we're basically taking that same technology and using it for different applications. So the leap in technology is not as much as one would think. It's just that we're reprogramming it to do something else.
I have a question about the patentability of nanostructures. Are they considered something you can patent?
Yes, you can patent them. They've been patented like crazy over the last few years. So it's very difficult now to patent things in nano. A few people who've gotten a lot of they captured a lot of the, the patents that say, anything that's, of this size scale that goes into the body, or, So there's some very broad patents out there. I think now people are sort of honing in on very specific areas. But yes, it's patentable.
So I think that's an interesting note to end it on. So we're hitting right up around 9 o'clock now. So I want to thank one more time our speaker for coming out today. I'm sure we all have had our interest piqued during this. So thank you again, and I'm sure Kishore wants to plug in his next.
I'll plug a couple things. Number one, Rich back there. Wave your hand, Rich. He has a email sign-up sheet. If you haven't signed up, go ahead and do it. There's also a donation jar that Herb is holding up that you're welcome to contribute in any way, shape, or form. Next month, third Monday next month, we'll be talking about psychoactives in your brain. We're going to be talking about ecstasy and the neural pathways that it uses. It's actually really interesting. It's not just about how to use the drug correctly. It's about understanding the basic ways our mind works. And I want to thank Adam and Tejal again from the bottom of my heart, especially. I want to remind you to go to the website sciencecafesf.com. There'll be.
As we would have predicted. What's more is we went back and we started to look at animals collected from agricultural areas more carefully, not just at their gonads. And we found that animals often look like this from agricultural areas, so that should be a liver. And that, I love this slide because that looks like a smiley face wearing sunglasses. So but what it is, this is a slice under the microscope. Each one of these lumps is a slice through a cestoid worm, a parasite. We looked at other animals, and these are the kidneys, these two things. Here's kidney tubules, but all the rest of this kidney is filled with trematode worms, another parasite that actually swims up the urinary tract and infects the kidney. So we proposed the following, and we'll get to California to test this in just a minute. We proposed that environmental stressors might affect the stress axis, and we've actually shown this in publication. So for example, if the temperature goes up, and the pond dries up, and the animals become really crowded, their stress hormone levels might go up. These could be natural events, or these could represent global climate change combined with draining wetlands for agricultural purposes. There's interactions between these environmental stressors. So the pond dries up, and I already showed you the pesticides become more concentrated. As you activate your stress hormones, you mobilize the fat-soluble pesticides, which add to the water-soluble pesticides, increasing your stress response. And here's what I believe is important about the model. As you increase your stress response, as as we've shown in the laboratory. You damage your immune system, which leads to disease, which can lead to individual death and population decline. And what's more in the field is because your immune system's lowered, you end up with parasitic damage to your liver and your kidney. Here's what's significant about the model. If you were poisoned, one of the two most important organs in your body, your liver to metabolize the poison, and your kidney to secrete it. But here we have a model where pesticides lead to a stress response that damages the immune system, which leads to damage to the liver and kidney. So not only do you have a high pesticide load, but you can't get rid of the pesticides, which effectively increases your internal pesticide load. And of course, the more pesticides you have, the more corticosterone or stress hormone you have, the more damage you have to the immune system, the more parasites you have. The more parasites you have, the more you see, it's sort of a vicious cycle. The other thing that's significant about the model is, if I were just a wildlife ecologist, without the laboratory data that I've shown you, I wouldn't see the role that pesticides are playing in population and maybe even in global amphibian declines. Because I would go to a pond and I would see frogs that didn't metamorphose in time and dried up. I would see frogs that couldn't find food. I would see frogs that got eaten. I would see frogs that got diseases. I wouldn't see the intricate role that pesticides are playing in all those negative interactions. So the lab, the interaction between lab and field studies are very important. This is just to point out that other people have shown similar immunosuppressive effects of pesticides. So for example, the limb deformities that you may have heard about are caused by parasites probably, not by pesticides, but it's been shown that the host that carries the parasite, snails, other labs have shown that atrazine lowers immune function in snails, so they carry more parasites. And then a study in 2002 by Joe Kiesiger showed that atrazine lowers immune function in frogs so that they get more of the parasites that cause the limb deformities. So another study showed similar things. And in 2006, the study showed that atrazine increases ranavirus, a virus susceptibility in another species of amphibian. So we're not the only ones who are making these suggestions. The next question is, and I'm going to stop here for questions, is all the arrows and stuff look nice, but how do we really prove in the real world, in this landscape, that there are really these interactions between environmental stressors and pesticides? And that's the next set of work that I'll tell you about. Yes?
Okay, well, before we take one question, we're going to take a set of questions and then take a break. Is that okay?
Sounds good to me.
All right.
Or actually, why don't we do this? Why don't we take a set of questions, and then let me do one more section, because that's going to end all of my frog stuff. And that'll be a more natural.
We're not going to talk about frogs in the second half?
No, I was going to talk about people in the second half.
Oh, okay.
Yes?
Are there more insects in the area where there's more pesticides?
Say again?
Are there more insects? Like, are the frogs and other animals less affected as predators when they're stressed because of pesticides?
So there's probably more broader ecological effects. So the question is about insects. So two things are happening that I'm not even measuring. One is the herbicides that run off into the water kill the plants, the algae, etc., that the tadpoles are supposed to eat. Okay, so in the real world, in the laboratory, we know it's just the pesticides, but in the real world, they're not only affected directly by the pesticides, but the food base for the tadpoles is going down because the herbicides kill the aquatic plants. In the real world as well, the insecticides are killing off the insects that the frogs would eat. So not only is there decreased growth because of the effect that I told you about, but ecologically, there's a decreased food base for both the tadpoles and the adults because the plants and the insects are being affected. And for some of those, somebody asked, for some of those pesticides, there may very well be bioaccumulation, just not for atrazine. Others of them probably are accumulating.
Are there any comparisons to Roundup with atrazine and Roundup because Roundup has such a good rep?
Yeah. We haven't looked much at Roundup. Another guy named Rick Relia has looked at Roundup and shown direct mortality, but he looks at levels that are 1,000 times higher. All these pesticides I'm talking about are still at 0.1 parts per billion. He's looking at 1,000 times higher. We are just now starting to look at Roundup, and supposedly with Roundup, it supposedly has a very short half-life, and I think the data supports that, so it does go away very quickly. But supposedly the chemicals that Roundup is mixed with, the so-called inert ingredients, are supposedly more harmful to frogs than the actual pesticide. And that's not my work, that's other work, work that's been published by others.
if I could show off for just a second. Just, at another Ask a Scientist, we learned that stressors are one of the main contributors to aging. So I wonder if there's any chance that these frogs are actually either look older at a person their age, or they die earlier.
In the real world, in the real world, I would guess they die earlier in part because of the decreased food base, both because of the direct effect of pesticides and also the decreased growth and increased predation. Although you might expect that their predators are often also affected by some of the same negative aspects of pesticide exposure. But also because of the immune failure and the higher parasite loads, I would guess that they would fall off and die much earlier. But it's a harder thing to measure in the field. But I'll show you some data in just a minute, which is why I don't want to stop for the real break until we get through about 6 more minutes.
Let's take one more question before we start ending the break. No questions. Okay.
All right. So here's what I want to do. I want to finish up the so-called lab field lab model and show you why I call it that. Because again, we started in the lab, we went to the field, we came back and did a field simulation. The other things that we do in my lab, and these data are mostly unpublished right now and ongoing, is that we actually collect tens of thousands of gallons of water for multiple years at multiple sites and keep it frozen in the laboratory. So we can really thaw that water out and ask, for example, in 2001, when we saw 92% hermaphrodites, we supposedly, or presumably, have that chemical contamination captured, frozen in time. Then we can thaw that water out and ask, can we reproduce these abnormalities in the laboratory with that water? And then we have water from what I told you were clean years as well. So we have sort of a set of controls. And that's what I mean by lab, field, lab. We start in the lab, go to the field, and then we effectively bring the field back to the lab. The last little piece I want to tell you, I want to get to California, is that we sort of run the model backwards as well. Instead of bringing the field into the lab, sometimes we take the lab into the field. And here's what I mean by that, and this will get it closer to home. Here's our California stuff. This stuff is unpublished. It's the stuff that we're about to publish this coming June. We've been working in the Salinas, along the Salinas River, which flows this way, flows south and north. And California is very different. In the Midwest, 90% of the pesticide is atrazine and Roundup, or glyphosate. However, if you add up all the pesticide in Nebraska, Kansas, and Iowa, it doesn't equal the amount that we use in California. California is the single biggest user of pesticides for a couple reasons. One is all they grow is corn and soy in the Midwest. In California, we grow over 350 agricultural products are produced here. I don't know if you guys realize that. 50% of the U.S.'s agricultural products, 50% of the U.S.'s food comes out of California. Okay? And we grow year-round. So there's a lot more pesticide usage. And in fact, the Salinas River Valley produces 85% of the country's lettuce. Just this little short stretch, 85%. 90% of the almonds, most of the artichokes, most of the strawberries. So there's a huge amount of agriculture going on in a short stretch. This provided us with sort of a unique opportunity because the beginning of the Salinas River right here starts out clean. There's no agriculture. And it starts out relatively stress-free. So the water's about 22 degrees Celsius. It's about 1.5 to 2 foot deep. Very little environmental stress. 30 miles down the road, the river dries out. In fact, the river's dry through this whole stretch. This water is about 2 inches deep, about 100 degrees Fahrenheit, so about 38, 40 degrees Celsius. And the tadpoles, as you can see here, in this case, there's about 3,000 tadpoles in that one little pool. So they're experiencing what I talked about earlier, high temperature, desiccation, and crowding. So they're stressed, but still no pesticides. And then, as you get down near Salinas, it looks non-stressful again, right? 1.5, 2 foot of water, 22 degrees, so a relatively cool temperature. Except all of this water is agricultural runoff. 100% of the water is coming off of our food, basically. So, just to give you an idea what that looks like on Google, here's what it looks like upstream, protected San Padres National Forest, no agriculture. 30 miles down the road, here you can see the Salinas River, it's all dry. I mean, maybe when it rains there's water, but and apparently, because of agriculture, the water table is so low. Apparently, they pump water out of another river and pump it into the ground just so that they can have water for for usage for agriculture. Okay? So there's essentially no water here, and again, 100 degrees, 2 inches of water. And then further down, now you can see the difference. Okay? This is all agriculture, this patchwork. Here's the city of Salinas. So if we put that all in perspective, again, the water becomes more and more contaminated as we move down, and we can compare sites that are relatively stress-free, that have environmental stress, but no pesticides, and then finally have no environmental stress, but high pesticide and fertilizer loads. So we can really test that model with all those errors. So just real quick, if we compare the 3 sites, our model will predict retarded development. Okay? And that's what we see. If you're under environmental stress, high temperature, and pond drying or crowding, or if you have none of those, but just pesticides running off crops, your development is retarded, as is your growth. So just like our model would have predicted. Here's what I mean by retarded growth and development. As they say, a picture's worth 1,000 words. This animal's from the stress-free site. This animal's collected on the same day, exact same age, gestational age, same developmental stage, but it's in a little pool at 100 degrees, drying up with 3,000 animals in about a 5-foot radius. And this animal is in the same environment as this one, except that it's in all agricultural runoff. So there's a dramatic effect. Here's what I mean by bring the lab into the field. Here are 2 of my students. We literally took out cages, so instead of doing a lab experiment, we took out cages, and then we just picked up at each site 1 tadpole 30 times and put each one in these individual cages. Then what we did was, we wanted to test immune function, so we thought maybe we'd measure white blood cell count if we gave the animals an infection, see if they could fight it off. And so, I always joke, we injected them with a dangerous pathogen, but what we did is we just injected them with bread yeast. So we thought we were giving a benign infection that would, help us allow us to look at immune function. But what happens when you do that is the following. In Santa Margarita,